In 1897, Daniel Morehouse came to Drake University. He came to Drake because his college that he went to up in Excelsior, Minnesota, burned down, and he really wanted to continue his education. He came in 1897, which happens to be the same year that Drake accepted the delivery of a brand new telescope. The telescope was donated to the university by Francis Marion Drake, one of the founders of the university, and immediately they built that corner of the science building, which has the observatory dome. Uh, they didn't build a very good foundation because every time the trolley passed, the whole structure would actually vibrate. So, so in 1897, Morehouse was there, and he had access to the telescope. Through some uh, strange happenings, Daniel Morehouse became interested in science, and it became an obsession with him. He graduated from Drake in 1900 with a BS degree. At the same time, he also graduated from the University of Chicago, uh, kept on going to Drake and graduated in 1902 with a master's degree, and decided that he needed to continue his education. At the same time that Morehouse was buried in classes at Drake, a new tool appeared on the astronomical front. This tool was known as the HR diagram. What two scientists did, they collected all the information about stars, their color, their distance, how hot they were, uh, and they basically graphed them. And what they found was that most of the stars followed that line down the middle, which is known as the main sequence. And as you can see, the sun is somewhere in the middle of all that. This tool was a tremendous advance on how stars were looked at, but it still gave them no clue on how the sun worked. They had no clue about nuclear energy or anything that would seem to indicate that the energy coming from the sun was in a class all by itself. So they looked at the sun in awe. They also looked at the sun in the sky. I'm sorry, I got too involved. And they knew while they were watching the sun that it could not be a giant briquette of coal. It simply wouldn't have lasted as long. They figured that a briquette of coal the size of the sun would only last about 6,000 years. So it had to be something different. The idea at the time was the fact that what made the sun give off so much energy was the fact that it was a giant cloud of gas that was contracting. And the gravitational contraction of this gas was what gave it its heat. So, as with anything, as it contracts, the heat goes up. And given enough time, you have a very, very hot ball of gas. So they figured that the sun was actually contracting, and as it contracts, it gives off heat. They figured that given the amount of mass that was in the sun in its contraction would last about 200 million years. Well, this was certainly better than 6,000 years, but again, it didn't really answer the question. So they went back to the HR diagram and they took a look to see where the sun was, and it was a definitely a yellow white color. So they used another law, which was known as Passion's law. And Passion's law basically dictates the heat from an electrical reaction. Normally, it's actually a way of predicting what the temperature is on a carbon arc that would be ignited in hydrogen. Now, that's not something usual, but it's something that they used. So they would actually see where an arc would fire and they take its temperature. They found out that it was yellow, and this would indicate the basically the temperature and the heat, well, obviously the temperature and the amount of energy that the star was giving off. So this brought up another question. If light is is part of this heat, then what is light? You know, what is it that we see when we're looking at something that's illuminated? And of course, starting in the 1600s, lots of scientists put in their 2 cents. Francisco Grimaldi noticed that light had diffraction, it had deflection. So he was wondering if light was actually a wave. So it acts like one, so maybe light is a wave. Sir Isaac Newton took this one step further. He actually dispersed light into its different colors and noticed that he can take those different colors and actually recombine them into white light. So light could be both particles and a wave. Well, this didn't sit well with a scientist by the name of Kristen Huygens. He basically said light is a wave and there's no two ways about it. That's that. And looking at his hair, I'm sure he probably made fun of Sir Isaac Newton's hair, which was very straight. In the early part of the 1800s, Thomas Young, another scientist, said that light is a wave, and he performed something known as the double slit experiment, which proves it. It shows constructive and destructive interference. So light was definitely a wave. Then in 1905, Albert Einstein described the photoelectric effect, which makes light a particle. And he got a Nobel Prize for doing that. So obviously it has to be right. Um, well, so is light a wave or a particle? And you can see it looks like we have two different schools of thought here. But what I say, given the weather that's in Iowa right now, let's just sit back and have a sunny day and worry about what light is later on. But I mean, let's just believe that a sunny day is what we need. Anyway, if we take a look at what we get from the sun as far as light is concerned, we can see that light doesn't really have much in the way of a distribution in our spectrum as you might think. It only covers about, probably about 500 nanometers of frequency. But within that frequency, within that spectrum that we could, that comes from the sun, we actually see that. That's the limit of our vision. And if you take another look at what photosynthesis does, you can see that photosynthesis actually covers a good deal more. That's probably a good idea since most of our oxygen and a lot of our food comes from photosynthesis. So we have our uh, the natural spectrum of light. And as you can see, we have an awful lot more that goes off into the infrared that we can't see. So what is beyond the spectrum of what we get from the sun? Well, actually, until 1800, we had no idea. It took William Herschel. He was investigating light, and he decided he was going to take a look at the energy that was coming from different frequencies. So he set up his digital thermometers. Didn't know that William Herschel in 1801 had digital thermometers, did you? Well, anyway, he set up his thermometers so that he would be taking a reading of the various colors. And what he found was something beyond red. He had a thermometer that was registering beyond red, and it was actually registering a higher temperature than any of his thermometers. So he figured there must be a frequency of light that he can't see, and he called that infrared. Another astronomer, actually another scientist by the name of Johann Ritter, read about Herschel's discoveries, and he discovered he was going to take a look at the other side of the spectrum of light. He was going to take a look at the blue side. So he set up some light sensitive chemicals, and what he found was just beyond violet, there was a tremendous amount of energy that actually showed up in his chemicals, and he named that part of the spectrum ultraviolet. So here's the electromagnetic spectrum as it appeared around 1800. We have our visual spectrum, red, orange, yellow, green, blue, indigo, violet. The only reason why we have indigo is because it goes with Roy G. Biv. Indigo is a color that somebody thought up of and really isn't a part of that. Anyway, so we have Roy G. Biv as our spectrum. So if we take a look at when various parts of the spectrum were discovered, we come with a little bit of a hodgepodge. For instance, once again, Herschel discovered infrared around the year 1800. Ritter discovered ultraviolet around the year 1801. Then we have a bit of a jump here. According to what was his name? Maxwell. Maxwell discovered that there should be something that's a lot longer wavelength, but less powerful. And he actually called that a radio wave. And that's way down here. That was in 1885. A man by the name of Hertz actually discovered that. And now the frequency is called Hertz after him. Around the same time that Hertz came up with the radio spectrum, Roentgen actually came up with something called X-ray, um, and that was in 1895. They found that X-rays were actually, well, they were a little destructive. People actually got burned by some of these, so they were fairly powerful. But they also noticed that our bone actually stopped it. As a result, the ray could actually go through our skin, get stopped by the bone, and a picture of that would actually show bones within the hand or whatever. After this, uh, a we had several scientists. One of them, actually, Madame Curie, found that uh, radiation, in this case, gamma radiation, was actually a part of the electromagnetic spectrum, and that was in 1896. Then on the other side of the spectrum, we have the very long wavelengths. Uh, and so between the 1920s, 1960s, we have radio, we have electrical power, we have AM and FM. And in the meantime, 1940s, they found microwave. Well, actually, it wasn't called microwave, it was called radar. And radar came into effect. In the 1950s and beyond, they found that these electromagnetic waves could cause damage if they are powerful enough, like ultraviolet and up into X-rays and radiation, actually caused skin damage. And sufficient quantities of this radiation, they found, could actually kill you. But before it did kill you, in the 1920s and a little beyond, they found, well, some of the, shall we say, snake oil salesmen found that some of these rays could actually be beneficial. We do know that there are a number of species of animals that see well into the infrared range, and they do this in order to hunt their prey. Snakes, especially something called pit vipers, could actually stalk their prey and, based upon what they sense as heat, will attack. Dogs do see into the infrared, as well as some predators. We do know that infrared could see through dust. If you're looking, let's say if it's a foggy day, if you have something that could sense infrared, it'll actually look as though the dust or fog isn't even there, because it'll actually illuminate what is giving off heat. And so it'll see right through the dust or right through the water vapor. But getting back to the snake oil salesman, they found that ultraviolet will give you a glow of health. We call that glow right now sunburn, uh, because the ultraviolet rays will actually cause your skin to develop melanin, which will is actually a protection against uh, the ultraviolet rays. And you can see here on the right, here is a doctor using a ultraviolet probe to burn the inside of someone's nose, so they have some curing, some relief from um, well, uh, allergies. And of course, if you're, as long as you're getting an ultraviolet lamp, you might as well give a sunburn or at least a tan for Christmas. I'm trying to figure out what that guy is looking at. Then you have, oh, interesting. Okay, let's try that. So if we're looking at ultraviolet or infrared, we can see that infrared you can see infrared, at least as far as hot and cold water is concerned. You can see infrared as far as receptacle is concerned, and that's pretty important because if there is a lot of heat inside the wall, that can cause a fire. And finally, you can see where infrared, you can actually spot someone walking in a forest. Infrared is also used by single-celled animals. Uh, they actually obtain some type of a nourishment from infrared. They use infrared to grow plants on the International Space Station. And looking at an article that was in uh, Popular Mechanics, you can actually grow hair in 30 days. That's looks kind of silly, but NASA did find that red light therapy was an excellent way to take care of normal everyday pain. And then they found that Bosley hair restorer, uh, you can actually put this on your head and it will restore your hair. So infrared is needed for a whole variety of things. Just sitting in an infrared type of a chamber, a type of room, whoops, like a sauna, does help a great deal with your everyday tension. But you do have to be careful about getting too much infrared because infrared is also used to cook. And so if you were a little bit forgetful, you might set your readings a little bit high. Astronomically speaking, infrared is a tremendous help in finding parts of space that are invisible to the unaided eye. And in fact, infrared is exactly what's needed to take a look at the center of our galaxy, where there is a tremendous amount of dust. And using an infrared uh, telescope, one that looks in the near part of infrared, the center of our galaxy is easily seen. And you can actually follow the stars that are orbiting our black hole in the center of our galaxy. But the near infrared is one thing. If we are looking further into the infrared, we find that it is blocked, and it's blocked by our atmosphere. As a result, if we want to see things that are into the far infrared, we have to actually get above our atmosphere and take a look using different telescopes, telescopes that are in orbit around our Earth. And one of those that's going to get up there, hopefully this October, is the James Webb Telescope. It's going to orbit beyond the orbit of our Earth, and hopefully it'll point out it's actually 6 times larger than the Hubble, and it will find actually far distant planets because those are visible in the far infrared range. If we take a look at Jupiter, with the far infrared, you can see how active Jupiter is. And looking at other objects in space that are um, that are hidden from us by dust, using infrared actually clears out the dust, and you can see new planets being formed within those clouds. So having our electromagnetic spectrum and having it blocked by a lot of our atmosphere, we actually find that a lot of this is fairly helpful, because if we take a look at the ionizing part of our spectrum, we could see that's very, very well blocked. As a result, we are protected by our atmosphere from the really harmful rays of the sun, of faraway objects that are emitting high radiation. So it's a nice thing to have this atmosphere actually blocking out the ionizing part of the spectrum. So if we take a look at the ultraviolet, we have ultraviolet A and ultraviolet B. You can see that ultraviolet A actually makes it well into the skin before it is stopped. Ultraviolet B is actually stopped by the outermost layers of our skin. But if we do get high energy ionizing light, it will cause damage to our DNA. I can do that two different ways. One of them by irradiating water, which will affect our DNA. And the other one is the direct route, where radiation coming from high energy sources will actually, well, it will destroy the integrity of our DNA. It will eventually kill us. So our atmosphere is a good thing to have if we're trying to be protected by our atmosphere. Once again, taking a look at X-ray. If you ever noticed when you're having X-rays done of your teeth or any part of your body, they make sure that only the part they need to X-ray is actually exposed to X-rays, because uh, excess exposure to X-rays will cause DNA damage. Now we have other forms of radiation. We have alpha particles, beta particles. Now these are particles, high energy particles that are actually stopped by either paper or by the skin of our hand, or even our clothes. Gamma particles, gamma radiation is very high radiation. It is a part of our electromagnetic spectrum, and the only thing that stops it is either several inches of concrete or lead. That's actually dense enough to stop it. Neutrons are particles, and once again, they can go through paper or our skin. Most of the time, water will stop it. So what about radiation? Is it actually dangerous to us? Well, actually, it depends on who you talk to. Um, if you take a look at our non-ionizing radiation, traditionally, it's been told as being harmless due to its lack of energy. So we have all these things: computers, radios, cell phones, microwaves, uh, remote controls. All these things are giving off radio waves. And well, uh, theoretically, with the amount of energy that they have, they are considered to be, well, not too dangerous. Meanwhile, ionizing radiation will cause DNA damage. I'm going to skip over. You can see what they have for various radiation here. You can see that cell phones do give off some heat. They do actually have some type of radiation that can cause some damage. Uh, Microwaves will cause some skin damage. Uh, Light will is actually safe. Then you have ultraviolet, which will cause sunburn, X-rays, which will cause skin and DNA damage. And I think all of us have seen one of these signs going into a place where they have a microwave oven. It's dangerous to pacemakers. That's because it can upset how that pacemaker is set. So if we're taking a look at radiation, according to some, there are some dangers to radio waves and high energy electrical wires. The bottom part, it was actually a study done, and you can see that they actually electrical wires are considered to be safe actually up about a mile away. Um, and if you've noticed during the past years, they've actually cleared residential areas away from high transmission wires. Uh, the the debate on whether or not cell phones are dangerous continue, and they'll probably continue uh, for the next for years to come. So, do radio waves offer any kind of a benefit? Well, actually, way back in 1928, a scientist, actually a technician by the name of Carl Jansky, was given the task to find out why the under ocean cable was getting so much static sometimes. So he was trying to find the reason for static on the undersea cables. And what he found was the fact that there was a radio source that seemed to be following the stars. Well, first he thought it was the sun, but then he noticed that after a while the sun actually separated itself from where where the static was. And he followed it day after day until he found out that the static was actually being generated by the Milky Way. So this was the first instance where a radio source was actually known to be astronomical. Now, we are protected by most radiation by our atmosphere. But if you take a look at radio waves, you can see that the radio wave window is wide open. As a result, we get all sorts of radio waves from space. Now, while they are considered to be safe, there's an awful lot we can learn from them by building telescopes designed to look at radio waves. Now, how do you build a telescope that's designed to look at radio waves? Actually, it's the same way of building a telescope that's designed to look at observing optical waves, except that you're using a different type of gathering power with a Radio telescope, you have a huge reflector that gathers the energy and focuses it on a feed horn. So it's just like a telescope where the light is reflected onto an eyepiece. You have to take the light from faraway objects, radio sources, and feed them into, well, the eyepiece. In this case, there would be the sub-reflector and the feed horn. Those those impulses are then fed into a receiver where they are interpreted into a display. So here we have an optical view of M31, and here we have a radio view of M31. And you can see it does look a bit different, but you can definitely tell where the energy is. And you can see there's an awful lot of energy on uh, that galaxy that's right next to it. But everything else that isn't giving any radio wave on that. We've also taken a close look at Jupiter, and found that Jupiter has a uh, Van Allen belts similar to the Earth, but they are much more powerful. We also find that radio waves could actually interpret what we see as far as compounds are concerned. Now, compounds like water and other, uh, uh, I was going to say alcohol and others, actually do give off energy, and they could be interpreted by using radio waves. And here we have a radio wave that was able to see uh, ethyl formate, which happens to give raspberries their flavor. So if you're out there in space, you can actually find raspberry flavored alcohol. Not quite sure how much you would need, but it's out there. The other thing you can find out there is the remnants of the Big Bang. Two technicians, Wilson and Panzais, actually, once again, were trying to figure out why there is static, and they found that this particular static was every place they pointed their their radio telescope. And they figured out, actually with the help of several other scientists, that the signal that they were getting is the remnants of the Big Bang that happened almost 14 billion Earth years ago. So the larger you make your telescope, the more you'll see. It doesn't make any difference what kind of scope you're making. The bigger it is, the more you'll see. And of course, they made radio telescopes absolutely huge. These are the largest steerable radio telescopes on Earth. And of course, there was one bigger than this one that happened to be down in Puerto Rico. That was Arecibo, and that one was about 1,000 feet wide. Unfortunately, recently, uh, because of age and other things, Arecibo actually was destroyed. And now we have this telescope. This is actually in China. This is actually about 1,500 feet wide. And right now, there are contracts being written up so that uh, colleges around the world could make use of this. So the study of radio astronomy is going to continue. One of the things they can do to make radio astronomy even better is by taking not just one radio telescope, but actually taking two of them and sticking them some distance apart and then tying their signal together. Now, you can't just wire them together. You actually have to get them together at the exact point that they are in sync. So the signals have to be in exact phase to be in sync. So if we're looking at, let's say, with this, looking at this quasar, the telescopes have to use this particular phase and then get rid of this part so that the signal is actually in phase. So they've built telescopes, radio telescopes that are absolutely huge. We have the Very Large Array, which is actually uh, several hundred feet in diameter. We have the Very Long Baseline Array, which is actually about 4,000 miles wide. And then with this particular uh, telescope, again, we have all these radio telescopes working together and looking at M87. You can see optically, it kind of looks like a fuzzball. Using the Very Large Array, you can see that there is something on the end of that line of gas. And then by using the Very Large Baseline Array, you can see that there is definitely something that's very active on one part of that. About 2 years ago, 3 years ago, we had a whole Earth view, shall we say, a new type of radio telescope called the Event Horizon Telescope. And this was a global network of radio telescopes. It was literally the size of the Earth. And they took a close look at that very hot object on the edge of M87. And what they saw, this is the first time they were actually able to direct image a black hole. So this is a black hole. It is actually several times the size of our solar system. If you were to compare our solar system to this, it would be about that big. So this thing is absolutely huge. And again, something where a whole bunch of radio telescopes got together and were able to image something that is almost impossible to image. Several about 12, 13 years ago, something known as a fast radio burst was discovered. It was actually discovered by a local Des Moines astronomer. Her name was Laura, still is Laura Spittler. Laura comes from Des Moines, and she actually confirmed the existence of fast radio bursts. And her mother is celebrating a birthday tomorrow, so happy birthday. Anyway, enough of that. These fast radio bursts give off enough energy for in just a couple of milliseconds, that would be enough energy for a star to actually give off during its entire lifetime. So these are an amazing object, and we just don't know exactly what they are. So we're learning about that. So that's something else that we're learning from radio astronomy. But like I said before, we have our electromagnetic spectrum, and this is what is actually blocked by our atmosphere. So in order to see beyond what is being blocked, we actually have to get above it. And when we do get above it with smaller instruments, we find that there is well, quite honestly, a whole spectrum of information coming from stars. And so far, we have sent up uh, dozens of high energy probes in order to take a look at these objects that are giving off energy that we cannot see here on the Earth. One of those objects is the Chandra X-ray Observatory. It actually sees objects in X-ray. Now, what do we see when we see something in X-ray? Well, going around Sirius, we have a white dwarf star. You can see it there as Sirius B. Sirius B is giving off a lot of X-rays. And as you can see on the picture on the right, you can see how bright Sirius B is in X-ray compared to Sirius A, which is not giving off as much light, or shall we say information or energy, in X-ray. So is there more to this? Actually, fairly recently, we discovered another spectrum. And that spectrum is actually comes from gravity. When one object orbits another, it gives off gravity waves. Now, gravity waves are not real, well, they're actually quite small. They actually do they affect something well known. Well, it's hard to explain exactly what gravity waves are. We do know that we are affected by them. We do know that when they travel out in space, they affect the space-time fabric. And when they do that, they actually cause our Earth to distort. Not by much, several hundredths of an inch, but it's enough to be able to actually record that. So we have another spectrum of energy, and it's actually gravity waves. And how do we detect those? Well, we detect them by looking at the space-time fabric, and then having that fabric actually distort under the energy of gravity waves. So as the wave actually it actually goes through the Earth and makes the Earth flex. Here we have the first time gravity waves were recorded. And we have two gravity wave observatories, one of them in Livingston, Louisiana, the other one uh, the other one in Washington State. And as the gravity wave passed through the Earth, it actually distorted this, was called an interferometer. In other words, what it did was, we have Livingston Observatory, we have Hanford Observatory in Washington State, and then the gravity wave actually traveled like this. If we took a look at it, they actually took the signal and it was shifted by 7 thousandths of an inch, actually 7 thousandths of a second. Why did it have to be shifted by 7 thousandths of a second? Because since gravity waves move at the speed of light, that's the time it took for the gravity wave to get from Livingston to Hanford. So when the information was shifted by 7 thousandths of a second, it was no doubt that it was actually the gravity wave that caused the Earth to actually flex under this tremendous amount of energy. If we could see gravity waves, they might look like this. Now, these are definitely not a part of our EM spectrum. This is actually a whole spectrum unto itself. And that gravity spectrum looks something like this. Each of those uh, abbreviations is actually a type of star or a type of, uh, shall we say, a binary or a black hole or something that is actually combined or actually destroyed and caused this emission of gravity waves. So we are right now looking at this gravity spectrum possibly the same way that Morehouse was looking at the uh, HR diagram in 1900. And we are going to learn how to use this spectrum and learn about gravity and learn about how our universe is affected by and how it's controlled by our gravity spectrum. Okay. Next week, we're going to be taking a look at the physics of astronomy and how things have changed since 1900. And it's startling.